I would like to say hi to everyone, to thank you very much to join us today. My name is Maria Josefina Cuello, and on behalf of the EAGE local chapter of Stavanger, I will be chair the session today. The first talk of our local chapter for this term of the year is held by Khushbu Havilia. She will present her talk about integrated machine learning and physics-based workflows, qualitative and quantitative insights on monitoring carbon capture and sequestration. So thank you very much, Khushbu, to stay with us today and to present your work. Just a little bit of information before I start. This meeting will be recorded. Then we will have the presentation, and at the end, we will have a time for questions. I invited you, if you prefer to raise your hand and ask, you can do it. Or if you prefer, you can write it down on the chat box, and then we can read, we can go through the questions, and Khushbu will answer them. And then I will mention some final remarks at the end. So stay until the end, and you will know what's going on with the local chapter of Stavanger. Thank you very much. Khushbu Havilia, her background is geology, but she's working since but for more than 9 years at Schlumberger as a geophysicist. She is the product analyst for in the team of geophysical interpretation and Schlumberger. So Khushbu, the virtual stage is all yours. When you want, you can start with the presentation. Thank you very much.
Thank you, Josefina.
You're welcome.
So good morning, good afternoon, good evening, everyone. I'm Khushbu Havilia, working at SLB, as Josefina has mentioned. And I will be giving a talk on rapid qualitative and quantitative insights on CCS monitoring. So using rapid and integrated workflows to get insights.
Please, I will try to mute everyone until the end. There's someone with the mic open. So yeah, thank you. You can continue.
So before I start, just to give an overview of general CCS workflows that we have in any particular field. So a typical CCS workflow is divided into several steps, as you can see over here. So we start with generally regional screening. So we are looking for either depleted oil fields or depleted hydrocarbon fields for CCS for the carbon capture and sequestration. Or we can also look for saline aquifers where we can store the carbon. So the regional screening is a step where maybe in the hydrocarbon fields, you might have more data already existing. But if we are looking for some saline aquifers, so this is something we can do with 2D lines, a few exploratory wells. Once we have selected a few areas, then we do feasibility analysis on those areas, where we see whether those areas are initially like good enough to store CO2. There are several things we need to see, whether they are porous enough, whether there can be any leakage. So those feasibility analysis can be done to further sort out some of the fields that we have screened. Then we can do detailed subsurface characterization on these fields that we have selected to have a better understanding how much porosity is there, how much CO2 volume can be stored. And then we perform risk assessment of these selected fields, where we can see that when we store CO2, so once as we continuously store CO2, then even if a seal was originally present, there could be a structural deformation happening, subsidence happening, that could lead to the breakage of the seal. and then the CO2 will leak from the subsurface. So we need to do this risk assessment to see how much CO2 we can store, for how long can we store, because our goal here is long-term storage of CO2. So we don't want to store CO2 that leaks in short term. Once we have finalized which fields are good for CO2 storage, then we go ahead with the CO2 injection. And then after CO2 injection, our work does not stop at that point. We need to continuously monitor the CO2 in the subsurface. This is key to ensure effective storage of CO2 so that there is no leakage. And if there is any leakage, it can be quickly highlighted and can be stopped. So this subsurface monitoring is critical, and the presentation and the workflows that I will discuss today will be focused on the subsurface monitoring. So we have applied and tested the workflows on the Schleipner gas field, which is in North Sea. And for this data set, I would like to thank Schleipner Group and data publisher Equinor for the data, the open data that is available to test these workflows. This gas field is present in North Sea, as you can see the location of the gas field. And this is the coastline for Norway. And then we have the United Kingdom somewhere over here. And CCS operations have been ongoing in this field since 1996. We have multiple seismic data also available from different timestamps. So data acquired in 94 before the CO2 was injected in this field, as well as later on in 2001, 2006, and so on, to monitor the CO2. So as you can also start to see that in this two data, we already see a difference in the amplitude that is highlighting the CO2 injection that has happened. Some of the workflows we tested in this field were like basic initial workflows, like just amplitude analysis and seismic blending. We also tried out geoscientist-driven machine learning assisted horizon mapping in this field. We also tested AVO workflows and time-lapse inversion in this field to see how it can be useful. All these workflows that we used, it gave us comprehensive information on the CO2 spread in each of the sub-formation in this case, and how the CO2 volume is changing with time as more and more CO2 is injected in the subsurface. Apart from the seismic data from different vintages, we also had two wells available for this study. So well 1 and well 2, as you can see over here, well 1 is a vertical well, most likely an exploratory well, and then well 2 is a highly deviated well, which is the injection well, which was used for CO2 injection in the formation. And we had basic logs like gamma ray density logs like these available in this field. Based on this logs, we can quickly see the geology of the field. So this is the top Utsira formation that you can see over here. This is the main zone where CO2 is being stored. So it is a sandstone. It's a porous sandstone, as you can see over here, with thin shale intercalations, so around 1 meter thick intercalations, which divide this sandstone into several levels. So 9 levels have been identified in this sandstone. And although these layers, they act as flow barriers, but they do have some permeability. So they do act as potential fluid pathways, so that when CO2 is injected at the lower levels, the CO2 percolates upwards. So these thin shale layers divide this into different layers, but still they allow CO2 passage through different layers. There is a thick shale present on the top of Utsira, as you can see over here. This is also a little bit permeable. This also allows some of the CO2 to leak to this sandstone that is present above this shale. And above this, we have one more shale. This acts like a seal for the whole CO2 containment in this field. So to start with, as I mentioned, we had seismic data from different timestamps processed at different timestamps as well. And we chose to work with data from 94, 2001, 2004, and 2006, the data acquired in these 4 years, and they were processed together in 2007. So we wanted them to be processed together so that there is consistency in the placement of the reflectors in all these seismic volumes. So we chose to work with this data set for our workflows. So the first thing we did was we interpreted the top and the base Utsira formation in all the different surveys that we had, different time surveys that we had. This was done to understand whether there are any structural changes happening through time in these surveys. So as you can see over here, we have the horizon, the top Utsira two-way time horizon over here, and 94. So 94 is before the CO2 operation started. And then in 2006, after a significant amount of CO2 had been injected. So this is the two-way time surfaces. Then we also generated confidence attributes from our horizon interpretation, like how confident our ML model was in order to pick these horizons, so that you can see over here. And we do start to see some structural changes happening in these two-way time surfaces between these two surfaces. So what we did was we created a residual or a difference map between the different timestamps, like the surface interpreted for 2001 and the surface interpreted in the 1994, and started to plot them over here. And this is at top Utsira level, which corresponds to the level 9 of the CO2 plume. So we also had a polygon available for the CO2, for the level 9 spread of the CO2 plume, and we tried to match these differences with this plume. And it was clearly evident that those differences that we got in the horizon or the structure were quite conformable with the CO2 plume that was there for level 9. And these differences in some fields could be due to real deformation. That means there is some subsidence happening, some changes in the structure happening, which could lead to this changes in the structure with time. Or it could also be apparent deformation. So that means the structure is not actually changing, but the velocities are changing, which is leading to the change in the two-way time, and hence the change in the structure. So in this particular field, probably it was more a case of a apparent deformation, and there were some velocity changes happening due to the CO2 injection, which led to the changes in the structure that can be seen over here. But this workflows definitely can be helpful in other fields to identify real deformations as well. One thing we also saw was amplitude brightening happening after CO2 injection. And this in the two-way time horizon, it is not that evident, but if we look at the confidence attributes of our horizon, then we can see this very high confidence streak over here marked in this dotted line. So which clearly is because there was an amplitude brightening, and the amplitude is so strong that the model is quite confident in picking it up over here. So after we had interpreted the horizons, we started working with some of the rapid workflows. So I will go through these rapid workflows that can help, as I mentioned, in CO2 monitoring. These are quick methods that can be used when we are doing initial analysis and doing a monitoring of CO2 in the subsurface. So obviously, as you saw that in the amplitude itself, we can start seeing the changes happening after the CO2 injection. So we can run an RMS amplitude on top of the seismic amplitude. And these are the 4 time vintages we have here: 94, 2001, 2004, 2006. So this is one of the cross lines through the survey. And you can see that in the RMS attribute, we are highlighting all these areas where the CO2 is being injected and CO2 is being stored. So although RMS is a very qualitative kind of attribute, so we cannot quantify anything. And because it's RMS, it is also not, we also see a decreased resolution because it is doing RMS of a particular window. So it does not give us a lot of information, but it starts to give us information on the spread of the CO2, the lateral spread of the CO2 in the formations, as well as how the CO2 is changing with time. So if we compare with 2001, we do see changes here, but then we see more lateral spread happening in 2004, then more spread as well as more amplitude brightening happening in 2006. So it's good for giving us a quick analysis of the CO2 in the subsurface. So apart from RMS, we can also use an RMS attribute. So it is a repeatability attribute. So whenever we have time-lapse seismic data, as we have in this case, then we can understand its repeatability, like how similar or how dissimilar is this time data that has been acquired at different time steps. So that is what repeatability attributes do. So an RMS is the normalized root mean square attribute that can be used on the seismic. And you can see, so what it also uses, it does not run on a single volume. It needs a base survey, which will be 94 in this case, because that's before the CO2 injection started, and then the subsequent surveys after the CO2 injection. So We calculated NRMS for 2001, and this is for 2006. And again, we can see that there are differences in the seismic compared to the base survey, which was before the CO2 injection started. So it also gives us a good and quick information on the CO2 spread in the subsurface. But NRMS has some limitations. So some of the studies are there which say and clearly highlight that even if we have a repeatable reflectors of consistent data, we might still get high NRMS values, and that you can also see in this data. So definitely we expect high NRMS value in the Utsira formation of the CO2 injection. But below base Utsira, we are not doing any CO2 injection. So we should not be getting a high NRMS value in this area, but here we are getting. So these could be due to small changes happening in the reflectors structure, small changes happening in the amplitude below base Utsira due to the change in the velocity on the Utsira level after CO2 injection. So we have to be careful when interpreting any NRMS attribute, that whether these values that we see are truly highlighting the changes or it's just a small differences that are getting amplified. Another quick way to do an analysis of the CO2 spread is RGB blending. So what we have done is, as I mentioned, we have 9 levels in this particular field. So 9 levels of CO2 spread, 9 levels of CO2 plume that are being generated. So we blended the different time volumes, amplitude volumes from 2001, 2004, and 2006 at different time steps. So this is at the Utsira top itself. And we can see this is the CO2 plume that is getting highlighted, and it has a good match with the structure as well. These structural contours that I've displayed in all 4 are from Utsira top. But then we did some stratal slicing and we checked the RGB blending 30 millisecond below Utsira top, which will be another plume level, then 70 millisecond, which will be another plume level. So different plume levels. Again, the structure displayed is Utsira top. So the structure of the different plume levels below the level 9 will be slightly different, not exactly fully conformable to Utsira top, but it gives us a general idea that this is the CO2 spread and it is following the structure very well. And this, apart from just giving us an idea of the spread at different levels, it also gives us an idea of the spread through time. So all these blue colors that we see, they are coming from the amplitude volume in 2006. So that means these are highlighting the areas where the CO2 spread later on in 2006. So we can start to see that, okay, initially in 2001, we had CO2 in this area, then it started spreading outside as more and more CO2 was injected in the subsurface. So apart from doing an analysis of the amplitudes through RGB blending and other options, we can also do some AVO studies in a particular field. We can do a quick AVO analysis in which we can generate intercept and gradient volumes. In this particular field, we generated the intercept and gradient volumes using Schwe's approximation. And here we can start to see, so 94 again before the CO2 injection, so we don't see anything in both the intercept and the gradient volumes. And then in 2006, we can start seeing changes in the intercept. So the values of the intercept are increasing, the values of the gradient are increasing. And we can also, again, make out the different levels in this particular case. So the 9 levels, they are quite separate out in this case, as well as we can see the lateral extent of these 9 CO2 plume levels being captured here. We also see some velocity push down effect over here. As you can see, some of these zones, they look like they are concaving downwards, but that is more because of the velocity changes and again, apparent deformation of the structure. One thing we noticed was where in the formations where we have CO2, we saw a positive intercept and a negative gradient in this case, but we did not have the shear log available to us to verify from the well data whether this is what we expect. But that is a good thing to do in case you have this data, if you have the DT rho B shear logs available to check at the well level what kind of intercept and gradient is expected, and then check in the seismic whether you are getting the same values or not. Another thing that was observed was that the intercept is more continuous than the gradient. And that could be because the alignment of different angle stacks that we have, the near, the mid, the far angle stacks that was used for this analysis, whether they are properly aligned or not, as well as there's a frequency drop that we see when we move from near to far angle stack. So that can also affect the gradient computation and make it less continuous. We can also run some advanced workflows like time-lapse seismic inversion. So as I mentioned, we have angle stacks here, near, mid, far, 3 angle stacks. And again, when we run a time-lapse seismic inversion, it requires a baseline volume, like from which we will compare, which will be again 1994 in this case, before the CO2 operations. And then we can calculate the ratio of change, like how much these properties. So when we run inversion, we get P impedance, VP by Vs density, these kind of elastic attributes. So how much these elastic attributes are changing with the CO2 injection. So in 2001, 2004, and 2006. So the ratio of change actually measures how much it is the ratio between the P impedance at this particular time versus the baseline. So whether we see an increase or a decrease in P impedance happening. So we see a decrease in P impedance happening for the different levels that have CO2, as you can see over here in red. Again, the velocity pushdown effects are even more apparent in some of these volumes, as you can see clearly here. We see this sag kind of apparent deformations that are coming out of this analysis. So right now, till now we were looking at the cross lines, in lines, just looking at the spread and the different levels into these sections, but we can also extract them as 3D, and that is what we have done over here. We have used these ratio of change volumes that we got from the time-lapse seismic inversion, and we blended them while extracting them as geobodies. So this helped us in not only identifying the different plume levels. So as you can see, we have these different plume levels, these CO2 plume levels that are being separated out here through the volumes that were used. And again, the RGB blending helped us to identify how the volume or how this plume has spread through the time, from 2001 to 4 to 2006. So some of these areas in middle in white are the ones which were initially, where initially the CO2 injection, after CO2 injection, initially the CO2 settled actually. And then the blue on the edges, again, the CO2 that spread further in 2006 as more CO2 was injected into the field. This is the well 2, as I've showed in the beginning, which is a highly deviated well. So CO2 was injected probably in the lower formations and it percolated upwards through the thin shale barriers that we have in this particular formation. So all these analyses that we have done, they were quite good for a rapid analysis in a particular field to do a CO2 monitoring. Some of the additional analysis that we did was, for this analysis was only done for level 9, the plume level 9, which was at the top Utsira formation, not for the other zones. We tried to see whether we can estimate the amount of CO2 that is there in the subsurface for this particular plume, so plume level 9. So we stacked the seismic amplitudes along constant contours for this purpose to just identify, to see whether we can identify a contact. And again, this is an assumption that we are making, that once the CO2 has settled, so first assumption that we are making is that CO2 has settled well in level plume, level 9 plume, and as well as that the contact is horizontal. So this is some assumptions that we have made in this particular analysis. And what we do is we stack or average out the amplitude along particular contours, and you can see the result over here. So this is the initial RMS amplitude that was input, and this is after we have stacked the amplitude along the contours. It gives us a general idea where the contact would be in case, again, the contact is horizontal. So it gave us a general idea of where a contact would be in 2001, in 2004, and in 2006. And once we had an idea of the contact, we tried to calculate the pore volume. We did not, for the pore volume, we took the porosity from different literature and studies that were done in the field. We could not get any information on the CO2 saturation for the particular levels. So we could not actually calculate the volume of CO2 in the subsurface. So right now we have only calculated just the pore volume that is potentially occupied by CO2, but definitely if information on CO2 saturation is available, it would be good to integrate that in the analysis to get the actual volume of the CO2 in the subsurface. And because we are making so many assumptions in this particular case, so we did not just want to calculate one single pore volume for one particular year. We added some uncertainty to it. So uncertainty in the contact, so that the contact we are getting from the stacking is not fixed. It is variable by 1 or 2 meters. So uncertainty like that, and that the porosity is also variable between 5% of variation in the porosity as well was considered for this. So we got uncertainty curve rather than a single pore volume for each of the year, which you can see over here. And at least we can see that from year 2001 to 2006, how much, at least in the percentage, the CO2 amount is changing, even though if it is just a pore volume that we have calculated in this case. So I would like to conclude that for any successful CCS operations, monitoring of CO2 is very critical. So we can use rapid workflows like the ones I've shown here in order to do a quick analysis on the CO2 spread in the subsurface, how much CO2 is there, lateral spread, different vertical spread as well. So such kind of rapid workflows can be applied to do a qualitative and quantitative analysis. Definitely time-lapse seismic data was used in this particular case, and that is required to do these rapid analysis. It is one of the most effective ways to monitor CO2 in the subsurface. There are other ways as well. You can add tracers and all, but this time-lapse seismic data is also a useful way to monitor CO2 in the subsurface. And whatever workflows we have applied in the study can be also definitely applied in other CCS operations, slightly different based on the data that might be available to monitor the CO2 in the subsurface, as well as to prevent or mitigate any leakage that might be happening. So before I close, I would like to thank Surinder, Hilde, and Steve, who worked with me on this project for their inputs. And I would like to thank SLB for the opportunity to work on this project. I would also like to thank the Schleipner Group and the data publisher Equinor for the data that we have used in the study. So we have used the Schleipner 4D seismic data set and the benchmark model that are available, that were available. So thank you, and we can take a few questions now.
Yes, thank you very much, Kashu. You show us a really interesting presentation. I will just to say that for me, it's great to see how geoscience, geoscientist tools and technology can be used to transfer the knowledge and the information to support the energy transition. So thank you very much. I really like it. So I can start with the first question that we have in the chat. We have few minutes to go through it. So the first one is from Norman Urres. He asked, how does the plume extension relates to the closure of the structure that you initially had? Is there any place that shows leak or close to leak near the spill point? Thank you.
Thank you for the question. And just before I answer this, I would just like to reiterate what you said, Josefina, that all of these workflows, they are from the conventional hydrocarbon exploration and development world, and we can effectively repurpose them and reuse them in energy transition. So it's not that we have to make new tools and start from the beginning. So that is a really important point. Yes. Yeah. So as for the question, definitely some of these analysis that we done, like this one, when we are looking at the different plume levels with the structure, we can see that whether our plume is really matching the structure or not. In this particular case, we do see that, yes, it is following the structure quite well. Maybe here there are some points that look a little bit off from the structure, but this could be due to a little bit some uncertainty in the we have done this analysis in time domain. So this is a time structure. So it could be due to the uncertainty with the time. Sorry, this is the depth structure, but this could be due to some uncertainty in the time to depth conversion that might be leading to this. So right now, at least based on this rapid analysis, we are able to just match quickly whether it is following the structure or not, or whether there is some leakage happening at a spill point.
Great, thank you. So if someone else have a question, you can, okay, yes, I will read that. Hussein Ozdemir, I hope I pronounce well your name. If not, sorry.
That's okay.
Okay. Do you want to ask yourself or?
Yes, I'd like to ask myself, do you hear me?
Yes.
Yes.
We hear you.
Excellent. Okay. Well, that's a nice presentation. Thank you. Can you please elaborate on for the seismic inversion used for monitoring? How did you do it?
So when we run a 4D seismic inversion or a time-lapse seismic inversion, we have to give several inputs. So one of the obviously important inputs are the seismic volumes at different timestamps. So we ran inversion 3 times, so one for 2001, one for 2004, one for 2006 in this particular case. And the angle stacks from 94 acted as the baseline surveys, and then the 3 angle stacks we had. For example, if I go into 2001 inversion, then the angle stacks from 2001 were the 3 other surveys that were used. Then we need to do seismic.
Sorry, Javilia, Kushu, I have to interrupt you because we have 30 seconds to finish the presentation because we don't have more time on this Zoom meeting. So let me say at least until you continue to thank you all to stay here. I will share the email of Kashu on the chat box so you can continue the discussion by directly with her. And also, Kashu, can you go please at the end of the presentation where I would like to encourage and invite you to join us in the upcoming event that will be held by Egil Shalan, and he will present the deep sea mining, exploration and production challenges the 10th of November. So we have a EAGE local chapter Stavanger group on LinkedIn. You can join us, and also if you would like to share your work, if you have ideas and would you like to contact us and to share with the community, we kindly invite you to send